Hello, let's start the recording or lecture for the LiDAR-based object detection and segmentation. In the previous several classes, we already talked about the image-based computer vision solutions. We talk about the deep learning-based object detection, and also we talk about the deep learning-based segmentation. Since the success of the convolutional neural network, CAN, with the backbone and the neck architecture applied in many computer vision tasks, and we find that CAN is a very, very important and a very, very useful model. Now we need to think about, can we utilize this CAN model for LiDAR-based object detection and segmentation process? Because many of the autonomous driving, for example, you see the original autonomous driving from Google, from Waymo, from the Argo AI, from Cruise, they all utilize the LiDAR sensor. Different from Tesla, they're using camera only. But many of this companies targeted the L4 and the L5 autonomous driving, they all utilize the LiDAR. Now we will talk more about some of the latest vehicles that apply the LiDAR technology, but definitely this is one of the most important sensors for autonomous driving. And fortunately, to play and to design the algorithm for the LiDAR-based object detection algorithm, we have some famous dataset, similar to the Pascal VOC dataset, COCO dataset, and we have the KT dataset. KT dataset also have image data, but the KT dataset also have the LiDAR data. For example, the KT dataset is recorded using this kind of vehicle. And they have the original, the VALIDAR 64-channel LiDAR with 4 cameras. Camera 0, camera 1 are gray camera. Camera 2 and camera 3 are color camera. So you can see the location of the mounting location of the camera 2 and camera 3. So for 2D object detection purpose, the image dataset you get from the KT dataset, right, is always the camera 2. So if you want to play the 3D data, you can utilize the camera 3. But they also have a VALIDAR LiDAR. You can see sit on top of this vehicle. This LiDAR, they recorded all the point cloud when they collecting the driving data, and the camera and the LiDAR are recorded at the same time, and in addition to some of the IMU data. So the KT dataset is a very famous autonomous driving dataset. Many of the famous autonomous driving related algorithms, like 3D detection, even 2D detection, tracking, even mapping, are all based on the KT dataset. Right? If you need to develop a new algorithm, people always say, what's the performance when you validate your algorithm on top of the KT dataset? So KT data is pretty old data, but it's almost like standard evaluation dataset in autonomous driving for both camera and the LiDAR. Although recently we have Waymo dataset, we have Argo AI dataset, but these dataset are very new, but very high quality. So we will play with Waymo dataset in our homework, and we will introduce the Waymo dataset later. But for the KT dataset, you will find many of the existing algorithms are all doing the KT dataset. So you will find all the datasets are organized in the folders. They have the training folder and the testing folder. So the content of the training folder and the testing folder are very similar. The training folder, they have image 2 folder with different ID with PNG images that's coming from camera 2, the major color camera. You also have the images coming from camera 3. You also have the label. Then in the VALIDAR folder is the LiDAR bin file. So this is a bin format file, and you also have additional calibration. In KT dataset, the coordinate of the VALIDAR and the camera actually are different. You need to apply some of the coordinate transfer for the LiDAR if you want to apply the LiDAR on top of this camera, or if you want to do some fusion for the LiDAR and the camera. So we actually have one open source GitHub project actually have a very detailed tutorial of the KT dataset. We can stop sharing. We can see the Okay, so this is over GitHub repository. So we talk about the basic setup. I talk about the basic setup of the KT dataset and the definition about the KT bounding box, KT 3D location dimensions, kind of the annotation format, and what's the calibration data looks like. Like they have P0, P1, and the translation from validate to the camera and IOU to the validates. So you see some of the definition of this. And also we talk about how to project the LiDAR to camera, since they're actually in different coordinate. So here we showcase one example. We project the LiDAR on top of this camera. Also, we can show the 3D bounding box on the image. The LiDAR 3D bounding box on top of the image. So you can see this kind of the 3D bounding box displayed on top of the image. Also some basic image projection, kind of the philosophy. Also, you can see the 2D bounding box, the projection results. So this is our dataset, our GitHub repository talking about the KT data. And here we list the different folders. For example, we have a notebook talking about some of the visualizations of different data, including Waymo. And we also have the KT folder, talk about how to download the data set, even draw the LiDAR bin file using the Open3D or convert the LiDAR to a standard format like PCD file. So this is how to play with the KT dataset. Okay, let me share the PPT again. Okay, so KT dataset is not only about this camera and the LiDAR, so used for training. They also have a sequence data. Sequence data means it's recorded like a video, that is continuously, because many algorithms may utilize multiple frames of the data to do the detection. So KT also has automatic task. So they have, that's another challenges. They recorded multiple sequences. You can do some of the maybe for a SLAM algorithm, mapping algorithm. You can use in this using this subtask. So that's why the subtask data is organized in the sequence. And this sequence data, the same sequence data for the validate and the image, they also have the image. You can download from automatic task. 00 means one sequence, and they also have 01 and others. But totally, they have the 00 to 10. They have additional annotation for the semantic annotation. Semantic annotation means that for every 3D point, they have the annotation. So, for example, some laser points reflect from the ground, so it will be labeled as ground. Some laser point reflect from the car, right? It's labeled as car. So it will differentiate all the LiDAR points. So what it belongs to, similar to the image segmentation, but this segmentation is for the 3D LiDAR. So this additional annotation is not available in the original KT folder. The original KT folder only have the label. Only has the label. Label only have the 2D bounding box and 3D bounding box. Don't have the segmentation. But the semantic KT, so they have the segmentation information. So they have the sequence 0 to 10. So total 11 sequence, they have the segmentation annotation. And the remaining sequence, 11 to 21, can be used for the testing. So because this sequence don't have the annotation. And the annotation is in the format of the ID.label. So this is the ID bin file is LiDAR file and related to the ID.label file. So this contains each point in a label in a binary format. So the label is actually a 32-bit unsigned integer for every point. So every laser point, you will have a data, is a 32-bit unsigned integer. So the lower 16 bits is the label. So it's like so talking about this label. Then so it's like about, for example, what's the class? Maybe this is a ground. Maybe this is a car. Right? Talk about this label. The upper 16-bit, is about instance ID. Instance ID is very useful for tracking, because when you detect object in one scene, one frame, you say, oh, this is one car. But if you have another frame coming here, you redo the detection. So it's very hard to say, oh, the bounding box in this frame, this is the car, then go to the second bounding box, they are belong to the same car. You have no idea for that, right? So because these two frames are independent detection. That's why we need to do some tracking, say, oh, this car in this frame is the same to the car in next frame. To do this kind of training for the tracking, right? You also need to say, oh, the instance ID in this two frames are the same. That means this belongs to the same object. So the semantic kitty also has the instance ID. So this can be used for the tracking. So in a different scale, you know, oh, this is belongs to the same object if they have the same instance ID. So this is also very useful. But if you only do a single frame segmentation, maybe only the lower 16-bit annotation data is useful. The higher 16 bits maybe not that useful. It's only useful for tracking. So this is the semantic kitty dataset. Yeah, so you can see some of these different classes. They totally have 28 classes, like a ground, structure, vehicle, natural, human, and other object. So this is some of the bigger categories. We also did some visualization under the folder for our GitHub repository. We can visualize. So now you can see, hey, this is the visualization results. Visualization results of the LiDAR. This is XYZ. This is reflection map, XYZ, and reflection strength, intensity map. And this is mapped into the range image. So you can see the cars are over there, and mapped when you run map to ranging images, the same car are over there. So here you can see the pedestrian. You can see the pedestrian over here, and in this one, you in the range image, you also can see pedestrian over here, so this is you can use to visualize different the scan of the kitty semantic dataset. You can see the LiDAR's 30-point cloud results. Also see the random images, what it looks like. Okay, so but how to do the LiDAR-based the detection or maybe the segmentation? The classical LiDAR-based object detection is you can see in the VIDA 2008 paper. Is LiDAR-based 3D object perception. So you can see the LiDAR. You can see it's like scanning in a 360 degree. So when they scan object, you can draw this bounding boxes over the object. Then you can get an occupancy grid. Occupancy grid is similar like in the previous class when we talk about Tesla. They also generate the occupancy grid. But how they generate occupancy grid, they have different approaches. Because after you have occupancy grid, that's like a bird's eye view of the map. Then you know how you can drive, right? So for example, this is the area is safe to drive, so you can safely drive over there, and there is some object over here. You should avoid the obstacle. So the occupancy grid map are very, very important for the autonomous driving. Then in addition to this occupancy grid, and we know LiDAR is very easy to generate this occupancy grid because all the LiDAR points are in 3D. Now you just do the mapping. After you detect each object location, you get the occupancy grid. So that's why LiDAR is very easy for the autonomous driving. And that's why many autonomous driving companies are like the LiDAR. Similar to images, the LiDAR also is very, very has some of the good LiDAR. Some of the latest vehicle LiDAR has a very high resolution. So you can see a car maybe have multiple points, and you can gaze on the points, similar like images. You can classify is it a car or is it a pedestrian. So it's not like the radar, very low resolution. You only know something is there. You also know what kind of object is there, right? That's why the LiDAR, similar to image, you also can do the detection, get the location, also know what's this object. You also classify this object. This actually brings lots of additional benefit. The original LiDAR paper, right? They talk about hand-labeled examples, or they using some hand-picked features to do the vehicle classify. So this is some of the traditional approaches. Since we really like CNN, convolution neural network, because in images, is really outperform many traditional computer vision algorithms. Like a Tesla, everything become neural network. So that's why we also like to apply the neural network for the 3D LiDAR data. And when you think about, can we utilize the CNN technology for the LiDAR? If we can utilize existing CNN technology for the LiDAR, that makes the life really easy. And we really can get lots of the performance improvement compared with the traditional hand-picked features, because CNN can automatically figure out the feature by itself. But when we really compare the data structure of the image data usually have H times W times 3. 3 is RGB 3 channel. H and W is an image height and width. So image data is always a high density. You have every pixel the data. But the LiDAR is different. LiDAR receive results like a point cloud. You get XYZ coordinate. Every point has XYZ coordinate. They may have additional features like the reflection strength. There are other features over there, but the key point is XYZ. It's kind of coordinate. And the distribution of the point cloud is very, very sparse and irregular. Because this is in 3D space. Sometimes this part has the object, sometimes this part has the object. So what you get from the point cloud is not like the uniform things like image, very high density. Point cloud, like the point cloud, for example, vertically, they may only have 16 channel or 64 channel. The density is low. And it's very sparse. Many points, many places, if there is open space, but there is no laser reflection, that means that's empty. If it is empty, then it is very sparse data. So if we naively just created and cut the 3D space cut the whole space into 3D spaces, then even many regions, or we call it voxels, many places even they just have the empty. It's empty. And CNN is not suitable for empty data. CNN is not suitable for the sparse data. So that's why if you apply CNN for this kind of sparse data, is inefficient and the rest of the resources. So there are some of the major type of the solutions. We may go through some of the major categories of how we can apply the CNN for the LiDAR. The easiest type of the solution is we can do the projection. We can project the LiDAR to the bird's eye view or to the front view. Bird's eye view is very similar to the occupancy grid map, like previously the LiDAR shows. We also can project this into a front view, like a previous image. We said we can overlap the LiDAR with the image. So now the LiDAR data looks like an image. If it looks like an image, then we can apply the existing convolution neural network-based approaches to extract the feature, detect object, and we also can potentially do the segmentation. So this is some of the basic approaches. You can do the projection. Many solutions, like including Baidu Apollo, and we also see other solutions belongs to that category. The second category is we need to play with the 3D raw data instead of simply do the projection to the image space. For the 3D raw data, we also can say either we can directly utilize the point input, or we can do the encoding, maybe divide it into a grid. We can utilize Vox as the input. So then in the 3D raw data part, we actually can also have additional categories. Right? One is based on the point cloud or the grid representation. One is the input-wise permutation invariance feature. This kind of feature is coming from the point net operation. Now, like a point net, they have a feature like input-wise permutation invariance. Because different laser point, if you do the order of this laser point, they all have the same XYZ. If you put all this data, push them together as a vector into some operation, the order, if you do some permutation of the points, does not matter. That's why it should be it's it's called input-wise permutation invariance. Based on this feature, researchers from Stanford, they actually designed the operation called point net. Point net is a very interesting solution. They can extract the feature from the point cloud. But the one problem of the point net is computational-wise is very heavy. So that's why it's usually applied to a small region. And we can divide that into grid. Then inside this small grid, we can use point net to extract the feature. Otherwise, extract using point net for the whole 3D point cloud is very, very heavy. Yeah, so we will talk about some of this major type of the solution, how we can process the LiDAR data. Okay, so we talk about some of the basic category of the solution. But in terms of the task, we mostly have two tasks. One is 3D segmentation. You can get so some LiDAR pointer, where's the load, where's the cars. This is 3D segmentation. We also have a task called 3D object detection. 3D object detection is similar to the 2D object detection. You need to get the bounding box, the location. But now the bounding box is actually in 3D. So we first take a look about the first task, 3D segmentation. Because 3D segmentation compared with 3D object detection, the architecture is really more simple. Now let's first take a look about some of the 3D segmentation application. Before we talk about the 3D segmentation, let's first review. You actually can see the same slides in the previous class. We do some basic review. What is segmentation, and what kind of neural network architecture we usually applied for segmentation? For example, in the previous class, we talked about this encoder and decoder. This is encoder and decoder network architecture. And we actually sharing this polling indices, because in this decoding stages, we want to do the deconvolution. If we know the location of the polling places, it will help the deconvolution process. That's why the segmentation usually have this kind of architecture. And the detection results, like this is a road, this is a curb area, this is a car. Now you can see all the cars are using the same color to segment. So that's why it didn't detect the individual object. It just classified all the pixels belong to which category. If it is a car, then all the cars are using the same pixel. So it's not the object detection, it's just segmentation. If we want the object detection and segmentation at the same time, in the previous class we mentioned we need to using panoptic segmentation. Panoptic segmentation is we need to detect the object and the segmentation of the background at the same time. Now here we only talk about the segmentation. So this is one of the very famous work, encoder decoder architecture sharing the polling indices, and we can do the deconvolution. Another famous approach is called UNet. UNet is widely applied in the medical image segmentations, and many people also apply UNet for many segmentation tasks. If you see this UNet architecture, it's very similar, like encoder, decoder kind of the process. But instead of like previously, you sharing the polling indices, the UNet architecture, they actually do a copy and crop process. That means the input layer in the encoder process, there are some features you just crop the cropped version of the feature actually copied to the decoder. So it's like the similar idea like FPN. FPN you have bottom up and top down. Bottom up, some low level features are suitable for some small object, and then you actually can sharing this feature in the decoder stages, and then you apply some of the 3x3 convolution and the loop, then do the upsampling again. So this is the UNet feature. They are not sharing the polling indexes. They actually just crop the feature, sharing the feature to the decoder. So this is another approach, right? Some people also say you can add the feature into the decoder. because you are sharing the encoder's some of the low-level features to the decoder. That's also possible. So you can say segmentation usually have this kind of encoder and decoder architecture, including UNet and previously the segment net. Okay, so after the review of this 2D image segmentation, now let's talk about the deep learning-based 3D segmentation. One of the interesting work we want to talk is called the squeeze segmentation. Squeeze segmentation is about, for now, it's pretty old right now. It's several years ago. But it's a very, very classical approaches. And after the squeeze segmentation, they also presented the squeeze segmentation v2, and the latest, they also have squeeze segmentation v3. That's why we talk about the basic idea of the squeeze segmentation v1 and v2. Now we also talk about their latest version, the squeeze segmentation v3. There are three key components of the squeeze segmentation. Now they first do CNN, then they have the CRN called the conditional random field. Conditional random field is like an IN layer. This is widely applied in the segmentation part, make the boundary more clear. It's kind of the filtering process, make the boundary of your segmented objects more clear. Then finally you have some clustering, maybe a car maybe have multiple strong reflection points, but it actually belongs to the same car. So this is a strong reflection point, maybe cluster them together. Squeeze segmentation also have the open source implementation. You can see there are open source implementation for squeeze segmentation 1 and squeeze segmentation 2. Both squeeze segmentation v1 and v2 are implemented by TensorFlow, and there is TensorFlow 1.x, not TensorFlow 2. Now let's first take a look about the key idea used in the squeeze segmentation is they do the LiDAR data pre-processing, they do the projection. So we see traditional CNN is designed for 2D images. The squeeze segmentation idea is that they need to apply some of the projection for the LiDAR data so that they can apply the CNN. One of the easiest way is LiDAR data is typically in 3D. They have X, Y, and Z. But they can change this X, Y, Z. For example, one point over here, X, Y, Z. You can change it to angle. One is attitude, theta is attitude. One is to the north front of the vehicle. So you can use these triangles to represent one point. Then you actually can project this 3D point cloud into a 2D plane, like a 2D circle. Is a 2D plane. Yeah, we can see like this. It's like a 2D surface, right? So every point is X, Y, Z, but you convert it as 2 angle. So now all the points, whether they have different depths, they actually can be projected into the same depth, like in the circle. So this is the projection process. And in this 2D projection results and this region, you project it in the circle. You can flatten. It's like a 2D matrix. This can be height times width times the 3. 3 is the channel. So this is the basic called the spherical projection process for the LiDAR, so that you can get the random images in the 2D. After you get these 2D images of the LiDAR, then you can apply the CNN. So for example, so this is like a projection results. This is, but in addition to only using the, only getting the one feature, because every location you get one position in the circle, right? Because since the RGB images, you also have 2D image, you also have RGB 3 channel. So for this LiDAR data, to avoid the information loss, you also need to add some additional feature into the channel C. X, Y, Z can convert to H and Y, but then you can add some additional information into the channel C. Some additional information, maybe you can simply add this coordinate, X, Y, Z coordinate. Coordinate can be the feature for each point. You also add the intensity. the LiDAR reflection, each point has intensity, whether it is strong or weak. Also, they calculate a range, like a distance to the LiDAR point. So you add this 3 point, 1 and 1, total 5 features together as the channel. So the channel has 5 features. Then these 5 features, then you can compare with the camera view, because it's projected in the front view. And you can potentially align these points on top of this camera view. You can compare with camera view. The backbone of this squeeze segmentation, because it's a segmentation task. So now you can see this is still follows the encoder and the decoder process. And they also utilize a lightweight CNN to achieve similar accuracy like AlexNet. So the signal segmentation, some of the convolution layer is coming from the squeeze net. They're using the squeeze net for the extraction, feature extraction. Squeeze net is used to reduce the complexity. For example, they call the phi module. Compared with the traditional 3x3 convolution, like in the VGNet, right? It's always 3x3 convolution. The computational cost is lower in the phi module, because in the phi module you first have squeeze, 1x1 convolution, channel reduced by 4. You squeeze the feature. Then you do the 3x3 convolution, expand the feature by half. This is the expanded layer. Then finally concatenate them together. You have the same channel number output. So this is the phi module. And the phi module compared with the computational cost and the parameters are significantly reduced compared with traditional 3x3 convolution. And so that's why it's also using the phi module in the encoder part. For the decoder part, so they have it's similar like the phi module, but they have the deconvolution, like upsampling by the 2 times. But they still do the squeeze, reduce the number of the channel, deconvolution, then expand the channel, then concat, so that you can have the same. You can have the same channel output. One thing in the encoder and decoder process is like since the LiDAR, the range image is a very, very wide image. Because the laser scan in the horizontal level, they have very high resolution. Vertical level, because they only, depending how many laser beam they have. If they only have 16 laser beam, then they only have 16 points. So that's why in the vertical level, the resolution is very, very low. So that's why this kind of the encoder process, they didn't reduce the size in the vertical level. They only reduce the size in the horizontal level. You can see they reduce size in the horizontal level. So that's why in the decoding process, when you do the upsampling, so the Y's horizontal, there's no change, but the Y's is become 2 times, it's become wider and wider. So in the encoder part is wider, become narrow, and narrow. Vertical part, because the height part, there's no change. So this is some of the difference compared with the LiDAR's encoder decoder module and the compared with the traditional image based. Image has high resolution both in H and W, but the LiDAR they have very low resolution in the H. So that's why the squeeze net only downsample the Y's, and they utilize the layer 1 to the phi 9 module from the squeeze net for the feature extraction. And they use the skip connection to add upsample the features to the lower level feature map of the same size. So for example, they have this feature added them back. This is similar idea like in the UNet. UNet also adding this encoder features into the decoder part. So this is very similar. It's add back. So it's similar like the UNet's encoder and decoder architecture. finish the convolution backbone, encoder-decoder architecture. Then they have applied another layer called the conditional random field. It's kind of IIN layer. It's used to make the boundary better. Now we are not jumping into the details of the conditional random field. It's popular in the natural language understanding. So let's take a look about what's the conditional random field. What they can do. In terms of the original information, you can check this paper. So the purpose of the conditional random field is refine the coarse output of the label. For example, you have coarse output of the pixel-wise classifier. The boundary is not that good. So now you go to this conditional random field and make the boundary very sharp. Clean the boundary. Similar in this paper. Conditional random field as recurrent neural network. In this paper, they have this one. They utilize a fully convolution network. Fully convolution means they only have convolution layer. We know convolution can extract the feature, can extract the feature, right? Since the feature, the major feature, if you do the training, this is the L path. So after the convolution layer, they have a heat map. Heat map, like the image looks like this. So there is a field like you can directly output the convolution output. Instead of go to the fully connected layer, you output the different classes and the bounding box. They can simply utilize the convolution output, refine the boundary, like based on the conditional random field, then reshape the boundary. You can get the applet. So this is the major purpose of the conditional random field. So conditional random field applied in this squeeze segmentation network is try to refine the boundary. Then finally, you also have the clustering period to cluster different objects. Yeah, so this is the training results based on the tensor board. You can see after the training, so you can see the boundary looks much better. So this is a label. Yeah, and this is the ground truth label and compared to the predicted label map. So this is the squeeze segmentation result. Okay, now a new paper based on squeeze segmentation called RangeNet++. This is called the fast and accurate LiDAR semantic segmentation. Similar to the previous squeeze segmentation architecture, the RangeNet tried to utilize the backbone from the darknet 53 because they think Euro is very famous. Euro's darknet 53 backbone is also very useful. So instead of using the squeeze segmentation 5 module, they utilize the darknet 53 as a backbone. So that's why the other idea is very similar. Shrink the horizontal. You can say vertical height, no change, but width reduced by 2, reduced by 4, reduced by 16, and finally you reduce by the 32. So you reduce the width and apply the residual block similar to the darknet 53. Then do the decoding part. Decoding part is very similar also similar to the UNet, right? This feature can be added into here, then together to the upsampling, and other lower feature can be added to here, Then finally, you have this segmentation results. So this is one contribution. The contribution is they change the backbone, utilize idea from the darknet. This paper also have a second contribution is the post-processing. Instead of like the conditional random field used in the squeeze segmentation, they build a new post-processing algorithm. And this post-processing algorithm based on the nearest neighborhood. This is in the 3D GPU accelerated nearest neighborhood. And they find that this is actually much better than the conditional random field results. Because the previous squeeze segmentation, the conditional random field applied is for 2D image. It's for 2D image. So the segmentation result is in the 2D. Similar like this. Semantic segmentation result is that's in the 2D. but the actual segmentation you need to have is in the 3D. So you need to project the 2D range image back to the 3D point cloud. But the problem for this range projection is usually like original light point cloud in the 3D, but when you project in the 2D, now some of the points are overlapped, some of the points are blurred, especially the boundary. If you have the segmentation in the 2D, if you remap to the 3D, you will find that there are many boundary, especially there are some black shadow regions, because some of the regions, they may be mapped to the same points. Then in the segmentation, for example, 1.0 here, there may be multiple laser points from different locations, but all mapped to the same class in this 2D range image. Then you reflect, change back to the 3D. Then you'll find that this is actually in a different object, right? In the different places, but it actually belongs to the same object. So only apply the conditional random field to the filtering in the 2D space. Sometimes may blur the CNN output. So that's why this also try to do the k-nearest neighborhood things as a post-processing algorithm in 3D. So without things in the 2D, because in the 3D, you go through all the points. The points has there, right? Then you can actually, based on this semantic segmentation results, you can assign which class is more close. They can assign this point to a more close point. Then you can make sure all the points in the 3D data can get their classes. Yeah, so this is a basic process. Semantic, after they have semantic segmentation, right? They also have the raw output. Now, after the raw output, they do some filtering to filter out some of this error points to make the filtered results much better. So they also claim that they have the 3 steps. One is transform image into a range image representation. This is the projection process. Then you have the 2D fully convolution semantic segmentation. Then you convert the 2D to 3D back, recover all the points. Then they do the post-processing, clean the point clouds using the GPU-based k-nearest neighborhood search for all the points. So this is this work is done by the RangeNet Plus. Okay, so starting the RangeNet Plus. This is a relatively new paper, only 3 years ago. So RangeNet Plus, they have implementation in PyTorch. This is actually a very good implementation. If you want to play with 3D semantic segmentation, you actually can check this RangeNet Plus segmentation. Because later on we will say grid segmentation V1 and V2 based on TensorFlow 1.x. It may be too old. But the RangeNet Plus is based on the latest PyTorch. Then grid segmentation V3 is actually based on the RangeNet code. So that's why if you want to play with RangeNet Plus, I saw in their code they already implemented the V1 and the V2. The grid segmentation V1 and the V2 is already included in their code. And the grid segmentation V3 is actually based on the RangeNet Plus implementation. So that's why this belongs to the same latest implementation based on the PyTorch. If you're interested, you can check their implementation. Compared with grid segmentation, they replaced the CRF, conditional random field. But in the code, they also have the CRF implementation. You actually can check using their GPU-enabled k-nearest neighborhood search is better, or using the conditional random field is better, because all these are implemented in their code. Because they say k-nearest neighborhood is directly to the points in the point cloud space, instead of the 2D ranging images. Many things are blurred. Okay, now let's quickly take a look about some of the major code and the code structure used in the RangeNet Plus. First, in the users the Python file, they can specify what kind of parser pass the dataset. Also, what kind of the segmenter, what kind of architecture you want to use. This is 2 major things you set up in the users code. To pass the data, you actually can see the code on the semantic dataset KT parser. So you have class called semantic KT, and inside the semantic KT class, you represent each laser scan using class called the thin laser scan. This is another class. Thin laser scan is implemented over here. Inside, this is for lasers representation. So inside the thin laser scan, you have class laser scan, contains laser with XYZ and refraction, and a semantic laser scan class with XYZ and with additional labels. So this is the data structure for the LiDAR data. Is the thin laser scan. And the pass function linked in the user's code actually utilize the semantic KT class and created the train loader based on the touch data loader. You get a data set. This is how you can get to the passing the laser data. The laser data is defined in the thin laser scan with the label, and you have data set class, semantic KT. It's a kind of the PyTorch data set, and you are using the PyTorch data loader, get the train loader. So this is the training pass. And inside the laser scan class, laser scan is the representation for X, Y, Z, and the R, and the reflection. This is the data structure for LiDAR points. The projection code is inside the laser scan. You can see this dual range projection. If you want to use the range image, you can using the dual range projection function get the range projection of the LiDAR. It's actually inside the data class. Next, we talk about the model architecture. Model architecture is in the class segmentator, is a class. And inside the class segmentator, to the Python, you actually load the backbone, loaded the decoder. The backbone is the CNN backbone is the encoder. You also located the decoder location and also located the header. Header is the segmentation header. For the decoder, they actually implement multiple decoders like a degree segmentation V1 and V2. You actually can see the darknet segmentation, darknet decoder over there. You can select the either darknet, squeeze segmentation VB2. You can select the backbone for darknet decoder, also select the darknet. Then in the trainer, you can specify the pass, segmenter, then training. You can start the training by setting the model. The major trainers code in the trainer.python file. In the inference.python file, you actually can simply using user.infer. User.infer is user's class. This class user. This class user is only for inference. So you can using this user to do the inference. What kind of model you want to use? Using the model configuration file is in the architecture. What kind of data set configuration you are using? You can utilize the label configuration file under this folder. So this is pretty clear structure of this RangeNet purpose code. Okay, so now let's take a look about the squeeze segmentation V3 paper. This is pretty new in the ECCV 2020. In the previous RangeNet purpose, they already identified some problem. When you project into the range images, many points might be overlapped. The classes you assign in the range images, when you project back to the 3D point, I mean, they belongs to the different the points, different locations. So that's why the boundary usually is blurred. So this is a major challenge of the range image-based approaches. Then squeeze segmentation V3 also identified some of the challenges. For regular image, the feature distribution is largely invariant. You have a distribution of RGB3 channel. For different images, the distribution of this color or feature distribution are similar. But for the LiDAR, the features are the angle information. So if you have different, since the LiDAR data are very sparse, when you project it, if you have a little movement, so the feature distribution changes significantly at different locations. So this is a significant one of the different things compared with the image. So that's why this also try to utilize a spatially adaptive convolution. So this is a kind of new operator. We will not jump into this new operator. This is pretty hard to understand. But the key idea is like this convolution. They change the backbone. This backbone convolution, they can process different parts of image with different filters instead of using the same filter for the whole image. But because the different parts have significant variance, right? They can apply the different filter in the different parts of the image to make it dynamic. Maybe some parts you have high density of the points. Maybe you have this filter. Some parts maybe we have very sparse points. This is maybe you have different filter. Using this idea, you actually can adapt to the feature variation. This is some of the key idea in the squeeze segmentation V3 paper. Yeah, so they list some of the main drawback of the random image representation. It's pretty hard for the neural network generalize of the object because the different size in the different random images, right? The object changes significantly. And CNN network, if you can detect the pixel depth, but previously we get the depth, for example, using the XYZ and the range, right? But the convolution neural network are not really designed to utilize this kind of depth information, depth feature, and that's why you still have the scale ambiguity. So because in the 3D you project into one plane, right? So the scale really changes. You have this scale ambiguity in this 2D. And the random image also suffer from occlusion. Because potentially some of the similar points, right, they actually can project into the same locations. So that's why they have this occlusions. Then traditional convolution filters didn't really deal with this problem. So that's why they have a new operation mechanism changed to the convolution backbone called SAC, spatially adaptive convolution. So the major change is in the backbone. Okay, so in the CVPR 2020, there's another new paper called the PoloNet. Different from previous the random image based projection. Random image is projected to the front view. Front view. The PoloNet projection is one type of solution to project a bird's eye view. But instead of a rectangular bird's eye view, they actually have a polar bird's eye view representation. Why they want to have this polar bird's eye view like this? Instead of like equally divided like a rectangular kind of the grid with equal space, divided and different grid. But they say the laser really far away, the density are very, very low. So that's why the laser points in this region are very, very low. But the laser points close to the car are high density. So if you simply using this grid, right, then in regions close to this one, then maybe some regions maybe have so many points. And if it's really far away, some regions maybe don't have any points. So this is also different from the traditional images. Is different region, they have really totally different density. So that's why they plan to do this kind of the PoloNet. So now you can say PoloNet is if it is close to the vehicle, the density of the point clouds are very high, then your grid size also small. If it's really far away, the grid size become bigger. Now you can see if you flatten into the 2D space, right? You can make sure each grid may have similar number of the points. That make it easy to fit with the convolution neural network. Because convolution neural network assume the image, the data are is not sparse. It's not like some places you have very high density, some places it's like missing data. The data should be uniform. Then after you have this kind of representation, each grid you have similar number of the points, and that's why you can make it more uniform. This is the first thing. The second thing is since it's kind of the polar representation, it's kind of in the polar grid. Traditional CNN is not this kind of shape. Now, traditional CNN is rectangular shape to the convolution filter, to the sliding window process. So that's why the grid design called it's kind of the ring CNN to the convolution in this kind of ring connected scale called the ring-based convolution. And this polar net compared with square segmentation V2 and the RangeNet plus with darknet 53, square segmentation V3 actually achieves this, and compared with square segmentation V3, right, and the polar net. So compared with other approach, you can say they even can beat the square segmentation 3 now in the symmetric KT dataset evaluation. So that's why among all these approaches, polar net is the best one. They have a better accuracy. Yeah. So first up, there's another thing in the polar net is after you have the polar grid, now you have divided individual grid, right? The square segmentation, what they did is when they matched to this random image, what kind of channel they have, right? They simply manually pick some X, Y, Z and range R and the reflection strengths. It's manually picked 5 features. But what the polar grid want to do is we're into using learning instead of using handcraft feature. Why using learning? That's similar like a deep learning idea, right? You can learn some deeper features, maybe much better than some of this handcraft features. So that's why they can using learning to learn some of the deep feature. So they can this deep feature you can capture the distribution of the points in each grid with a fixed length representation. So every grid you have a fixed length representation. So what they do is they utilize a simplified point net. It's a learnable point net. It's similar like CNN can extract feature from the image. The point net, as we introduced earlier, point net can directly extract feature from the points based on this permutation invariant kind of the feature, and it's learnable. The problem of the point net is they cannot apply for large area, large scale of the point cloud. So that's why they simply but they can apply this point net in a small grid. This is a small polar grid. So small polar grid using a point net to extract a feature followed by a max poly. The simplified point net contains some of the Fourier canonical layer, Bayesian normalization, and the rule layer. So they didn't quantize the input cloud along the z-axis. So that's why the learned representation represents the entire vertical column of the grid. The polar grid is like because it's a bird's eye view. They didn't do any downsampling, quantify the points in the z-axis, only using the polar net to learn the feature. And this is like one of the major improvement. They learning the feature, not simply using the handcrafted features. If you see the polar net's implementation, you can see here, and you also can check the CVPR's paper here. This is their major trend file. In the major trend file, they set up the BV UNet, then set up the model, point called BV net. This class is still similar to the previous RangeNet property. They're using SynKitty, get the trend point cloud dataset, and they can differentiate if it is polar model or traditional model. They have the different dataset. Then the network, right? The BV UNet is bird's view. They modified it based on the UNet, and they have traditional UNet and bird's eye view UNet in the network part. And the PT BV, they're using the point net to get the feature. then using the UNet. I think it's similar to like a previous introduction in the each grid, using point net to get the feature, then using UNet to do the segmentation. In the dataset part, you have synced dataset, Vox dataset, spherical dataset, and yeah, so this is some of the and you also have spherical maybe assignment, assign the points based on their angles. So this is in the dataset set part. Okay, so this is PoloNet. Okay, another new approach is last year, CVPR 2021, is called DSNet. DSNet, what they do is kind of the using a dynamic shifting network. So it's based on the dynamic shifting module. The dynamic shifting module is actually at the output. You already have this regression center. It's similar like a post-processing. After the post-processing, you get the instance ID. Then they combine with this scenes point mask. This is object detection part. This is pointwise object detection part. Then they get a fusion. Then finally get the panoptic segmentation. So this is kind of the panoptic segmentation work. Yeah, so we can talk about this panoptic segmentation work in the next class.